All right, we left off. We were doing molecular and empirical formulas. We did a couple of examples. Also related, structural formulas. And for structural formulas, we also have molecular models. So this is, I think, what I was alluding to when I was talking about there's different types of structural formulas. You can also model them as these like ball and stick models, which I think we'll get to play around with a little bit. So in the ball and stick model, we represent our atoms as colored balls, and they usually have holes in them that you can put in like little plastic pieces, little plastic sticks to connect the two. And they're typically color-coded. Sometimes the colors are a little bit different, but a lot of them are standard. So like hydrogen, carbon, nitrogen, oxygen are all pretty standard. I think sulfur and chlorine as well. Obviously, we can't do this for like all of our atoms because 91 colors is just too many colors for us to expect the average chemist to be able to, see and imagine and distinguish. So it's usually just, a simpler version. There's also space-filling molecular models like these. You can buy kits or packs that do space-filling models. So usually those will have like magnets or something on them, or they might just have a side that's like flattened off to show where you can attach a something. So this is our structural formula for CH4 methane. CH4 is the molecular formula, CH4. We can represent that with a structural formula where we've got one line indicating that we've got one bond. In our ball and stick model, we've substituted the letters for balls and colors, carbon in the middle. This gives us even more information than our structural formula because it shows us how the different groups are oriented to each other. And then the space-filling model is actually the best of these models because it shows us the way that the atoms actually kind of overlap in terms of their electrons and how they're sharing electrons. I believe we've got a lab where we'll be doing some stuff with molecular models later in the course. So we're just mentioning them kind of for now. Here's a couple of things, and their names, their empirical formula, their molecular formula, structural, ball and stick, and space-filling. Space-filling models aren't always the best because, like we can see with the benzene up here, it's a little bit hard to tell what's going on. For glucose, also kind of a little bit hard to tell what's going on. And so typically a ball and stick model or a structural formula is going to be better for representing those larger things. We also don't get to see like how many bonds we have between things. For example, for in acetylene, our carbons are triple bonded to each other, and we don't see that when we look at the space-filling model. So don't expect that we're going to be using a lot of ball and stick models, but you should hopefully be able to identify, hey, that's a chemical, that's a compound. And then maybe with a little bit of thought, piece together sort of what the empirical or molecular or structural formula might be for that. All right, we can break things down into pure substances. For all pure substances, we can break them down into either elements or compounds. We've done this before. We classified matter this way before. Our other option, other than pure substances, was mixtures. And so now we're going to go into elements and compounds. Starting off with elements. Our elements can exist as single atoms, like sodium, neon, etc. in our list here. A lot of our elements fall into this category of being just one atom existing by itself. They're separate from each other. Our noble gases will also do this. However, some of our elements exist as molecules. So their normal state, when you find them out in the wild, they exist as two or more atoms bonded together. We've got 7 that are diatomic elements. The di prefix here meaning 2, so 2 atom elements, diatomic molecules. And we've got others that are polyatomic elements. Polyatomic just meaning more than one. Or more than two, whatever. And if you were wondering, Mr. K, do we have to memorize these? Yes. Yes, you have to memorize these. Yes, you have to know these. But are you going to test us on them? Yes. Also yes to that. Yes, you will be tested on them. Okay, so starting off with our molecular elements. Here they are, our beautiful, wonderful molecular elements. We've got hydrogen, oxygen, fluorine, chlorine, bromine, iodine. There are a couple of mnemonic devices for remembering our diatomic molecules. So our diatomics, we've got up in the top left, hydrogen. And if we imagined the rest of these ones that are shaded in yellow on like a digital clock, what number would those be on the digital clock? 7. So we've got kind of a 7 shape. So H7. That's one of the helpful tricks. So just nitrogen to fluorine and then down to iodine. There's also Brinkelhoff. Brinkelhoff. Brinkelhoff is another mnemonic device for remembering those. So this is all of these diatomic elements. And then there's another one that is apparently not in the slides as far as I could see. Horses need. Any guesses? Oats. For, sorry, that should be capitalized. For clear, brown eyes. But it's the letter I. Horses need oats for clear, brown eyes. That's the third and final mnemonic that I have for the diatomic elements. I don't know, I'm not much of a horse girly myself, so I'm not sure if that's true, if horses actually need oats for clear brown eyes, but it's believable. Could have fooled me. And then I don't have anything for you for PSSE. Just they're polyatomic. They're inside the 7, so maybe that's a thing. Questions about any of those? Cool, fun, neat. We also have molecular compounds. Molecular compounds are typically composed of 2 or more covalently bonded nonmetals. So this is one of our subsets of pure compounds, pure substances, but on the compound side. So we've got 2 or more covalently bonded nonmetals. Molecular compounds are just nonmetals. The basic unit is the molecule. The smallest piece of a molecular compound is a molecule. And then there's some examples. So like water is made up of H2O molecules. Dry ice, which is carbon dioxide, is made up of CO2 carbon dioxide molecules. Propane is composed of C3H8 molecules. So the smallest amount that you could have of one of those compounds would be 1 molecule of whatever the substance is, H2O, CO2, or C3H8. Our other side of compounds for pure substances is ionic compounds. Ionic compounds are composed of cations, positively charged ions, usually a metal, and anions, usually one or more nonmetals bound together by ionic bonds. Usually, but not always, a metal. It will, however, always be a cation. There are a couple of cations that show up on the list of things that you have to memorize. Those are the ones that would show up as cations that aren't metals that would make it an ionic compound. Our basic unit, our smallest piece of an ionic compound, not smassest, smallest piece, smallest piece of an ionic compound is the formula unit. The reason that the smallest piece is a formula unit is because the way that these compounds actually exist is typically as one big chunk, and it's just repeating positive, negative charges, cations, anions, in 3 dimensions. So we don't have like separate individual parts like we do with a molecule in molecular compounds. So we break it down to what's the smallest repeating unit, and that's the formula unit. So the formula unit is also what the chemical formula is. Another thing with ionic compounds is for ionic compounds, we always write the empirical formula for ionic compounds. It's always the simplest ratio of the ions to each other. Many ionic compounds contain ions that are composed of other atoms, and they have an overall charge. And we call these polyatomic ions, the poly meaning many, atomic, of course, meaning atoms. So these are many atom ions. So it's not just one atom that's gained or lost electrons to pick up a charge. It's a bunch of them together that are sharing a charge. So for example, NaNO3 contains the sodium ion, and it contains this NO3 minus group. CaCO3 contains our calcium ion, and it also contains this CO3 2 minus ion. KClO contains K plus, the potassium ion, and ClO minus, which is a polyatomic ion. So our polyatomic ions are here. And we'll talk more about polyatomic ions later. First, let's practice classifying some substances. So we're looking at pure substances. We want to know, are they atomic elements, molecular compounds, or ionic compounds? So first up is fluorine. We could start by asking, is fluorine an element or is it a compound? Fluorine is an element. What kind of element is fluorine? It's molecular. It's a diatomic molecule element. What about N2O? Is N2O an element or a compound? It's a compound because we've got 2 chemical symbols in there. We know that there's 2 chemical symbols, partly because they're both capitalized, also because there's the subscript of 2 separating them. So we've got 2 elements in there. Is this going to be ionic or molecular? It's going to be molecular. We don't have any metals, and so it's all nonmetals. All nonmetals usually means that it's a molecule. So this is a molecular compound because it's only nonmetals. What about silver? Silver is an element. What kind of element? Atomic or molecular? It's atomic. An atomic element. Our molecular elements are only nonmetals. I don't know if you noticed that. So hydrogen all the way over on the left, usually lumped in with nonmetals, and then nitrogen through oxygen down to iodine, phosphorus, sulfur, selenium. Those are all nonmetals. So anytime that we've got a metal, it's going to be atomic. And then we've got K2O. What kind of elements do we have in K2O? What kind of element is K? Yeah, K, potassium, is a metal. It's over on the far left side of the periodic table. And oxygen is a nonmetal. A mix of metal and nonmetal means that we've got an ionic compound. So potassium's a metal, oxygen's a nonmetal, making it an ionic compound. How about Fe2O3? What kind of thing is that? Yeah, it's also an ionic compound. For the same reasons. Fe is iron. So rust is an ionic compound. Questions? Cool. All right, ionic compounds exist all over the place. We eat them. They also exist in the Earth's crust as minerals. They're generally very stable, very, very stable, because of the strong ionic bonds between the ions. These ionic bonds are full, positive, and negative charges. So they're very strong interactions between the cations and anions in the crystalline lattice. When we are writing formulas for ionic compounds, we write the symbol for the metal cation, or just the cation, with its charge, followed by the symbol for the nonmetal with its charge. This is just starting to write the formula. So we're going to figure out what's our cation, what's our anion, and what are their charges. And then we need to get the charges to balance. So we're going to adjust the subscripts on our cation and anion to get the positive and negative to cancel out. Our ionic compounds are always going to have neutral charges, overall at least. And then we can check that the sum of the charges on the cations equals the sum of the charges on the anions, but opposite. Our ionic compounds are always going to have positive and negative ions. The first element is usually a metal. The cation gets written first. And then the anion is written after that. So some ionic compounds might contain this ammonium cation, NH4+, which is also a polyatomic ion group. And our formula needs to be the smallest whole number ratio of ions. So basically an empirical formula. It's probably not technically correct to call it an empirical formula, but that's the idea. We want the simplest whole number ratio of the ions. So if we want to practice, we want to write the formula for the compound formed between these two things, potassium and sulfur. So we would need to know the symbols to start. So potassium is K. potassium, when it forms an ion, have we talked about how to get the charge of the ions? I think we have, right? So potassium, being in the first column, it's an alkali metal. Metals tend to give up electrons when they go through chemical reactions. It's going to lose electrons to get it back to the nearest noble gas, which is argon. In order to do that, it would need to move one space to the left to kind of wrap around to be on the argon spot, or lose one electron. So it's going to form K+. Loses one electron, which is true for everything that's in our 1A column. And then for sulfur, the symbol is S. So we find sulfur. It's in group 6A. So we can do 8 minus 6A to figure out what the charge is. Or sorry, 6 minus 8, whatever. Or we can count over to the noble gas column. So starting from sulfur, we count over 1, 2 spots. Now we're in the noble gas column. It's going to be a 2 minus charge. And then we need those charges to balance each other out, to be equal and opposite. So we can look at this. All right, well, we've got a 1 plus charge. We've got a 2 minus charge. We can't make the 2 minus charge smaller because we can only have whole numbers, so we can't have half of a sulfur. But we could have 2 potassiums, which would make the overall charge 2 plus. So if we have 2 K pluses, then that would be a total of a 2 plus charge, which equals the 2 minus charge on our 1 sulfur. So that's one way that we can go about doing it. There's another way, I've heard it called the swap and drop or the crisscross method. So K plus and S2 minus, we take the charge, just the number part of the charge, and make that the subscript for the other thing. So this would turn into K2S. Since potassium just has a charge of 1, sulfur would then just be 1 sulfur, and we would end up with K2S. The only time that we'll run into trouble, because we will sometimes run into trouble if we do the swap and drop or the crisscross, is if they have charges that can be simplified. So crisscross might need simplification sometimes. But the method does work. It also works for polyatomic things as well. If we want to do the charge or the formula of the compound that forms between aluminum and nitrogen, aluminum is in group 3A. Group 3A. And it's a metal, so it's going to lose electrons. It's going to lose electrons to get a 3 plus charge. That's the number of spaces that you'd have to move to the left, skipping this middle block, of course. The spaces you have to move to the left to get up to the previous noble gas. Nitrogen is a nonmetal. It's going to gain electrons in an ionic compound. It's in group 5A. It's going to move 1, 2, 3 spots over to become like neon, and so it's going to be a 3 minus charge. So this is one place where we would run into trouble if we crisscrossed. So let's see what that looks like. So if we crisscross them, we get Al 3 N3. Our subscripts are both 3, and we have to have the simplest whole number ratio, so we would get rid of both of the 3's, divide both of them by 3. So it would just be ALN. Many of us, though, could probably just recognize, hey, 3 plus 3 minus, those already balance each other out. Put them together 1 to 1, and you just jump straight to ALN. So you're welcome to always crisscross and sometimes have to reduce. Or you can just maths your way to it, if you like that instead. Now the fun part, the new stuff. Ionic compound naming conventions. So some compounds have common names like water, ammonia, rust, but chemists the world over have developed systematic names. So the way that the systematic naming system works, we've got 91 elements, plus some that don't exist all the time. You can imagine that there's billions of combinations, different ways that you can combine all of those different arrangements. Because of the billions or more of names that we could come up with for different compounds, our naming system has to be really precise. It has to be really exact in order for us to be able to tell one compound from another based solely on the name. So it's going to feel a little bit like our naming system is a little bit obtuse, a little bit hard to manage perhaps. There's a reason for that. So I will try to point out at times, like, here's why we're doing this for our naming convention, like here's how it separates it from other things. But it is a process to learn all the naming steps. So for naming ionic compounds, first thing we've got to do, we have to identify that we have an ionic compound. So we have to see that we've got cations and anions, or more likely that we just have metals and nonmetals together. So we're usually going to have metals and nonmetals, the exception being things like NH4+ would also count as a cation. So things like what we're seeing here. So these all have metals: sodium, aluminum, calcium, magnesium. We can organize our ionic compounds into two different categories. You're already seeing how this can be a lot of fun. So the first type of category, the first category is a metal whose charge is always the same. Charge is always the same. Or, like the slides say, whose charge is invariant from one compound to another. Just meaning, if we see that metal, if we see that ionic compound, that cation, it's always going to be the same charge. We never have to worry about it being something else. And then our other category, perhaps unsurprisingly, things that can have multiple charges, multiple charge options. So it can be different charges. So multiple charge possibilities. Not all at once, but within a compound, or within different compounds, it could have different charges. And generally, these are relatively easy to separate from each other. So these are the metals that are always going to form the same charge. So the ones that we've talked about before, unless I'm crazy, right, are 1A, are 2A, are 3A. So everything that's an alkali metal are alkaline earth metals and aluminum, and then a couple of new ones to us. We've got scandium. Scandium, very conveniently, is just one column over from calcium to the 2+. Still going 1, 2, 3. So scandium's a 3+. Very nice, very convenient. And then a little bit less convenient, the silver and the zinc that are over here. The way that I remember the silver and the zinc, and I think we'll have a slide about this, but I want to talk about it now anyway. If we look at aluminum, zinc, and silver as a little staircase, notice that the top step is aluminum. So the top step of this staircase is 3+. If we step one step down the staircase, now we're on 2+. You step one step down the staircase, now it's 1+. So as long as you can remember that that staircase is there, to think about it as a staircase, you'll be able to get that 3, 2, 1 down pretty easily. So when we're making ionic compounds with these, the name of the ion is the same as the element name. We don't change anything. So that's super nice. And that's because we know that it's always the same charge. We also have metals that form more than one cation. which includes these ones in this table, but is basically all of our transition metals. So everything, not including scandium, but from scandium over to zinc, not including zinc and silver and scandium. So all this middle block, anything that's in there, and some of the other stuff that's like tin and lead, thallium and indium and gallium, those would probably also fall into the can form more than one kind of cation. And we've got two naming conventions for these, or two naming rules. So one set of rules is classical, and that would be what's called older names up here, so chromous and chromic. And then we've got stock notation, named after, I think, Alfred Stock. So chromous refers to the Cr2+ ion. Cr3+ is chromic under the classical naming convention. And in stock notation, or the current more popular naming notation, especially in chemistry, these are chromium-2. So chromium and then parentheses Roman numerals for 2, which is II. And then we've got also chromium-3, which I know you can't believe it, chromium III. So that's the newer nomenclature. Part of the reason for learning the classical notation, the chromous and chromic, is that, like, particularly people that are going into an allied health profession, they apparently still use, like, especially for iron, ferrous and ferric. And so if you don't know that notation and then you're like in nursing school or in a vet program or something and they're using those terms, that could be confusing. And also that's just the way that the other instructors teach it. So the easier notation is definitely the stock notation, but you're not always going to see that. And also if you go back to older notation or older chemical literature, you're going to see chromous and chromic. The one thing that's nice about the older notation is that there's only two names, first of all, and the one that ends in OUS is the lower charge compared to the one that ends in IC. So OUS is the lower valued charge, the smaller charge, and the IC ending is the higher charge. The thing that's not nice about this older notation system is that, unlike with chromium, it's not always 2+ and 3+. So if we look at copper, it's copper 1 and copper 2+ that are cuprous and cupric. The names also change a little bit, so they're more based on like the original name where we get the symbol from. So that's why it's cuprous and cupric. And for tin, it's stannous and stannic. So you have to remember 2 ions for each of the metals. And then the lower charged one ends in OUS. The higher charged one ends in IC. So lots of good flashcard material here. The Roman numerals, in case you've forgotten your Roman numerals, you only need to know up to like 8 probably. We start off with 1 I, add another I, now it's 2. 3 I's for 3. 4 is not 4 I's, it's IV, the I in front of the V meaning we're subtracting 1 from the 5, V for 5. You don't have to put the bars across. And then we can add by putting the I after the V, so VI, VII, up to 3 I's in a row, and then IX and X. Again, probably 6 would be the highest that you'd need to go. Usually they don't go higher than that. Questions about these metals that form more than one cation? Cool. All right, some tricks. They're not my tricks, but some tricks. Metals in group 1A and 2A form ions with a charge equal to the group number. We talked about that already. The metals that are in this triangle are also predictable. I think this might also apply to cadmium, but I'm not 100 on that. But definitely this staircase method for the triangle works. 3, 2, 1. Aluminum, zinc, silver for that 3, 2, 1. And scandium is also a 3+. This would also be good stuff that if you have a study group, you could just kind of back and forth quiz each other on what the charges are. Anything that's not one of these ones that always forms one charge, just assume that we need Roman numerals or the classical notation, chromous, chromic, plumbus, plumbic, stuff like that. Moving on to our anions. We've got a lot of monoatomic anions, so where it's just one atom and they have a charge. Our monoatomic anions contain one atom, and they're named by changing the ending to IDE. So fluorine, the base part of that is fluor, F-L-U-O-R. We would change the ending to ide, and you can add the ion part after it as well. So that'd be the fluoride ion if we're talking about just F- by itself. The charges for these are all predictable. So counting how many spots you need to move to get to the noble gas column, fluorine is 1 over, so it's F-. Oxygen is 2 over, so it's 2-. Nitrogen's 3 over, so it's 3-. In case you were wondering, like, where does carbon play into this? Carbon's 4 from either direction. It doesn't really play those games. So it's just up to 3+ and down to 3-. You could also count backwards from the noble gases. So that's for all of our monoatomic anions. They're all just always the same charge, which is cool. So for naming binary ionic compounds, the easiest class of ionic compounds is binary, meaning that we've just got two things. So binary compounds are just two different elements. Our naming is going to be the name of the cation, followed by the name of the anion, changing the ending to IDE. Relatively simple, or it can be relatively simple. So for example, KCl has potassium in it. Potassium is always the same charge. So we just write potassium, because it's always going to be K+ when it's an ion. So we write potassium. Cl is the symbol for chlorine. Chlorine is always going to be the same charge as well. So we take the base name for chlorine, which is the chlor part, and we change the ending to IDE. Our name is potassium chloride. CaO follows the same convention. Calcium is always 2+. So we just write calcium. Our base for oxygen, which is ox, and change the ending to IDE. Oxygen is also always 2-. Questions so far? Lots of fun and definitely not stuffy rules. Very cool and hip and easy to understand. I think it's fun, but it's also a little bit like learning a board game from a friend who's way too into board games, and it takes 2 hours to set up the board game and then 12 hours to play it. It's sort of like that. So once you learn all the rules, like, it is really fast and relatively painless and easy. But until you get to that point, it is probably going to be a little frustrating. And just like with board games, the best way to learn, arguably, is to play the game. So we want to write the name compound Ag3N. First thing we need to do, what kind of compound do we have? It's an ionic compound. How do we know it's an ionic compound? Yeah, it's a nonmetal and a metal. Okay, so we're tapping into our ionic naming convention. How many ions do we have? How many elements do we have? 2. Just 2 things. I think that's all we're going to see. Just 2 things. So we've got our metal, we've got our nonmetal. So we're doing a binary ionic naming. How many ions, how many charges can we have on silver? Does it have 1 charge option or does it have multiple? Silver is the first step on our staircase that leads up to aluminum. So silver is 1, zinc would be 2, aluminum would be 3. So silver is always going to be Ag+. So it's always Ag+. So we just write silver for the silver part. And then for the nitrogen part, we need the base name for nitrogen, which is NITR, and then we change the ogen to IDE, IDE. Another piece of practice working the other direction, write the formula for rubidium sulfide. What is the symbol for rubidium? Yeah, it's Rb. And then sulfide, the ide ending meaning that we've got a monoatomic anion, just 1 atom of the anion. The sulf part is the base for sulfur. And sulfur has what symbol? S. This is not our formula. The thing that we've got to do now is figure out our charges. So Rb is a 1+ charge because it's in our alkali metals. It's our group 1a. Sulfur has what charge? 2- because it's in 6a. It's 2 groups over from our noble gases. So it's a 2-. So we can either do the mental math to figure out what the subscripts have to be for the charges to balance out. We could also crisscross. When we do that, we'll get Rb 2 S. And that would be our formula for rubidium sulfide. Questions? All right. There is another type of binary ionic compound. So if we have more than one kind of cation, this is most of the transition metal elements. So most of the transition metals instead of elements. Most of our transition metals can form more than one charge. So like chromium and iron and copper and gold. These can form more than one type of cation. So when we name them, we need to include the charge of the cation in Roman numerals in parentheses so that we know what the charge is. And the charge, if we're starting with the name, can be determined by inference. What we really mean here is math of the sum of the charge of the nonmetals. And we'll see examples of that. So this is kind of the same thing. We just have to specify what the charge is since it could be different things. So for CrBr3, what is Cr? Chromium. What charge does chromium have on it? Positive, but chromium shows up in our transition metals. It's not scandium, zinc, or silver. So we're not sure what the charge is necessarily. It could be a number of different options. So just to give us a placeholder to remember that it could have multiple charges, we'll add in the parentheses now, and then we'll do the anion. Br is the symbol for what? Bromine. The base for bromine is brome, and then we're going to change the ending to IDE, just like we did with our other type of ionic compound. Now we need to fill in the blank. We need to figure out what's the charge on the chromium. We know that the charge of the chromium has to balance out the charge of the bromine. Total positive charge has to balance out the total negative charge. So let's find out what's the total negative charge. Bromine has what charge when it's an ion? 1 minus. It's one spot over from our noble gases. So Br minus, and we've got 3 of them. So we've got 3 minus overall anion charge. We could also have written this instead like this. So we've got a 3 minus, because we've got 3 bromines, 1 minus charge each, so we've got a total of 3 minus. For our chromium to balance out this 3 minus, what charge does it have to have? Yeah, it has to have 3 plus. So in our Stock notation, named after Alfred Stock, chromium 3 bromide. In our older notation, our classical notation, chromic bromide. If I'm not misremembering. So either of these would be acceptable. They both say the same thing. It's just that one's a little easier to read. Questions? All right. Let's name the compound FeS. What is Fe? Iron. So Fe is iron. What charge does iron have when it's an ion? Does it have one charge that it can be, or multiple charges? It's got multiple, so let's start off with just some parentheses. Let's save space for the charge. What is S? Sulfur, so we're going to use the base, which is sulf. What do we change the ending to? Ide, I-D-E. So iron something sulfide. What's the charge on our sulfur? 2 minus. So if we've got our FeS, sulfur is a 2 minus. We only have one of them, so it's an overall 2 minus. We've got one iron. It has to balance out the 2 minus. So that's going to be 2 plus. So iron 2 sulfide, or ferrous sulfide. Using the classical notation, classical name. All right, let's work the other direction. We want the formula for ruthenium 4 oxide. What is the symbol for ruthenium? Ru. Ru is for ruthenium. And what's the charge on ruthenium? In this case, 4 plus. It tells us with the Roman numerals in parentheses. So we know it's Ru 4 plus. I'm not 4 plus, I'm actually 3 plus. But more on that later. Oxygen has what charge? 2 minus. So O2 minus. And then we've got 2 options. We can either mental math it or crisscross and simplify. So crisscross, this would make it Ru2 PO4. Can we simplify that? Yes. What do we divide by to simplify? 2. So this turns into RuO2. Which kind of has the cadence of like a cheerleading chant. Anyway, so RuO2. So that's not all for ionic compounds. We also have ionic compounds that have polyatomic ions. These are where we get some more of those ions that have to be memorized. The way that we do this is the same. So all that's changing is now we're using polyatomic ions. We just use the name of the polyatomic ion for the polyatomic ion. So we don't change anything about it. We just need to know what the name is. So an example, NaNO2 is named based on its cation, the cation Na+. Sodium always forms a 1+ charge because it's an alkali metal. So the name is sodium. And then depending on where we are at or in our memorization, we'd either look up or know that NO2- is nitrite. So this would just be sodium nitrite. The name of the polyatomic ion is important. The formula is important. The charge is also important because the charge is part of how we would get the formula from the name. So how we would go from NaNO2 to the name sometimes, or from the name to the formula. Here's some of the common polyatomic ions. Ones on here that would be definite, like these are ones that you will memorize. Carbonate, hydrogen carbonate, the hydrogen part. If we look at carbonate, it's CO3 2-. Hydrogen, when it forms an ion, will be an H+, a 1+ charge. So if we tack on hydrogen in the front, it takes away one of the charges. So HCO3- instead of 2-. And then the name is just hydrogen carbonate. It's also called bicarbonate. So you would want to know that it's also called bicarbonate. This rule applies, the add a hydrogen and take away one charge, applies to a couple of other polyatomic ions. Hydroxide, nitrate, chromate, dichromate, phosphate. We can do that same hydrogen thing with phosphate. So PO4 3- is phosphate. If we add a hydrogen in front, we take away one of the charges. Now it's hydrogen phosphate. With phosphate, we can do another one, H2PO4, and we've taken away another charge. To say that there's 2 hydrogens, we add di in front. So dihydrogen phosphate. Then we've got ammonium, chlorate, sulfate, permanganate would be something that you'd probably have to memorize. We can also have hydrogen sulfite. More on that later, perhaps. Cyanide, peroxide. Like in hydrogen peroxide, H2O2. The ones that I didn't write arrows next to, we can learn a system for coming up with those names. And for a lot of these, they're on your green sheet. So on one of the sides of the green sheet that I passed out, if you need one, I have more. We've got a bunch of oxyanions at the top. We're going to learn a system. It's the steps below it. We're going to learn a system for changing the number of oxygens for each of these to come up with some of the ones that I didn't write an arrow in front of. There's also a box below that that's got the normal ion name and then what happens if you add a hydrogen or 2 hydrogens. So it's not all pure memorization, fortunately, but it is a lot of memorization still. Most of our polyatomic ions are going to be oxyanions. So these have oxygen and another element. It'll always be the other element first. And we've got series of oxyanions. This is why I didn't put arrows in front of everything. If there's two or more ions in a series, the one with more oxygen atoms has the ending ATE. The ATE ending is the one that I recommend memorizing. The 8 ending, the ATE ending, is also the one that shows up on the green sheet in the oxyanions table at the top of one of the sides. So it's got all of them up there. You have to memorize the number of oxygens and the charge for each of those. If there's only 2, then the one with fewer oxygens will have the ITE ending. If we get more than 2 ions in a series, then we have prefixes for that. So we've got the prefix hypo. Can anyone think of a word that has hypo in it? Hypotonic? How about a less scientific hypo? Hypoallergenic? What does hypoallergenic mean? Any guesses? Less allergenic. So hypoallergenic products typically are for people that have allergies. So like hypoallergenic cats. I think there's some cat breeds, or dogs, or like different types of cosmetics or foods or other goods, perfumes. Hypoallergenic, meaning less allergenic. They cause less allergies. So the hypo meaning less, also like in hypodermic needle. And then per, like in hyper. If you're hyperactive, you're not just active, you're more than active, right? You've got extra energy. You need to go run some laps or something. So per, meaning more than, is also used. So 2 series. We've got chlorate and bromate. So here's our 8s. These are the ones that you'd memorize. ClO3 minus, BrO3 minus for a bunch of different oxyanions. From the 8 ending, if we add 1 oxygen, then we add the per prefix in front. So relative to our 8, we've got the +1 oxygen. We add the per prefix in front. What do we do with the charge? How does the charge change? It doesn't. The charge does not change. So that's one of the nice things about these oxyanion series. The charge is always going to be the same as the 8 form. So ClO3 minus, if we add 1, it's ClO4, still a 1 minus. If we go from our 8 form, if we drop 1 oxygen, so ClO2, we're minus 1 oxygen now, the ending changes. To ITE. So 8 is bigger than IT in terms of the number of oxygens. And how does the charge change? It doesn't. Charge is the same. It's still 1 minus. If we take off another 1 from our ITE ending, we keep our ITE ending, but we add a prefix. So we add the hypo prefix in front. So hypo plus the IT makes for a -2 oxygens relative to our ATE ending. So if you know the ATE ending, you can add 1, put the per prefix on there. You can subtract 1 to change the ending to ITE. You can subtract another 1 to get to the hypo and ITE ending. And this works for all of the oxyanions. So the one set of, like, what do you do if you plus 1, minus 2 oxygens applies for all of our oxyanions, assuming those oxyanions exist. So that kind of cuts out a reasonable number of things to memorize. Questions about oxyanions? Okay, and then here's just the rules. It's opposite of the way they show it in the text because it feels like it makes more sense to have plus 1 be above. So if you look at it in the book, it'll be the opposite way. But this is the recommendation. And the charge is the same. For all the oxyanions in a series. It's not always the same, like between oxyanions, but within the series, adding or subtracting oxygens, it's always the same charge. And let's do some practice. Okay, we've got the compound SNCLO. So SnClO3 2. What is our metal? Our metal is tin. So Sn is tin. What charge does tin have? It could be different things, right? So tin, we'll put some parentheses. Make some space for that charge to add in later. What is ClO3? ClO3 is chlorate. What charge does chlorate have? So we can figure out our tin charge. Yeah, it's a 1 minus, and we've got 2 of them. So we've got a total of a 2 negative charge. And to balance that out, we've got 1 tin. So our tin has to have what charge? Yeah, our tin has to have a 2 plus charge. And so we would call this tin 2 chlorate, or stannous chlorate in the classical naming. We also would like to write the formula for cobalt 2 phosphate, or cobaltous phosphate. Cobalt has what charge? Yeah, it's CO2 plus. The Roman numerals in parentheses lets us know it's 2 plus. And then we need to know what phosphate is. What's our formula for phosphate? PO4 with a 3 minus charge. So we can either crisscross and simplify if necessary, or mental maths it. I usually just crisscross it because I think that's what most people do. So when we crisscross it, we've got CO3, and then in parentheses, because we've got a polyatomic ion group, we've got our PO4, close the parentheses and put the 2 outside. So CO3, PO4, 2. Can we simplify that? No. So that's our formula. And I'm going to go a little bit further because we've got some more stuff that's related to ionic compounds, but do we have any questions so far? Confusions? Okay, we can also have hydrated ionic compounds. If I said that I was really hydrated, what does that mean? I've been drinking a lot of water. Or I've been drinking a lot of Celsius, which happens to have a lot of water in it. So hydrated ionic compounds, it's the same principle. Hydrated ionic compounds have water. So they've got H2Os that go along with them. Hydrate or hydrates means hydrated ionic compounds, or ionic compounds that have water within them. Sometimes we'll talk about them just as hydrates, partly because it saves time. So if you see somebody saying hydrates, we're talking about ionic compounds that have water on them. So these are ionic compounds that have a specific number of water molecules associated with each formula unit. For example, Epsom salts, MgSO4 middle dot, whatever that symbol is, 7H2O. That middle dot does not mean multiply, it means associated with. So every MgSO4 has 7 waters, H2Os, with it. And oftentimes hydrates of compounds like this, the hydrate form has a different color from the anhydrous or the without water form. So another word that we'll see alongside or related to ionic compounds is anhydrous. So anhydrous means without water. So what we've been looking at before this slide. Just if you don't have water, it's anhydrous. For hydrates, we use a prefix system. So we have our ionic compound part, we name that with our normal ionic compound rules. And then the stuff that comes after the dot is prefix for the number, hydrate. And these are some of the common hydrate prefixes. These can go up to really large numbers. We probably won't go above 10, but they can go into the hundreds for this style of numbering. So common hydrate prefixes, the weird ones here, Hemi. Hemi you've probably seen on like Chargers, Dodge Chargers or Challengers or whatever, muscle cars. Hemi Cuda, right? It's like a big beefy vehicle. The Hemi just means that the cylinders are opposite of each other. They're flat. They're firing across each other. I think that's what it means. So half. They're half a circle away from each other. Maybe that's how you can connect it. Hemi, half. Ones that you're probably more familiar with: mono, di, tri, tetra, penta, hexa. The weird ones, hepta. So pay special attention to hepta. Hepta is 7. And then octa, like the octagon or an octopus, is 8. Nona, that's not our Italian grandmother, that's 9. Nona starts with N, like 9 does. And then deca, like in decade, for 10. So let's name these hydrates. The first thing that we want to do, name the ionic compound part. What is Ca? Ca is calcium. What charge does calcium have? Does it always have the same charge, or can it have multiple charges? Always has the same charge. It's always a 2+. It's an alkaline earth metal. Shows up in our 2A or group 2. So it's just calcium. And then SO4 can, for now, refer to our green sheet or maybe our memory. It's sulfate. So calcium sulfate. And now the hydrate part. We've got a number in front of our H2O. That number is 1/2. Our prefix for 1/2 is Hemi. So calcium sulfate, Hemi, hydrate would be our full name for that. For our next hydrate, we've got BaCl2. What is Ba? Ba is barium. Barium also always has the same charge, so we just write barium. Cl is chlorine. So we write the base, chlor, change the ending to IDE. And for the hydrate part, we've got 6 6 is hexa because hexa also has X in it like 6 does. So this is hexa hydrate. And then let's try writing a formula. We've got copper 2 sulfate pentahydrate. What's the symbol for copper? Copper is Cu. What charge does Cu have? Yeah, it's a 2 plus. The charge was specified in the name. And what's sulfate? It's SO4, and it's got a 2 minus. So hopefully we can see we've got a 2 plus, we got a 2 minus. Put them together, they're already balancing each other out, so it's a 1-to-1. So CuSO4. And then what do we need to put before the hydrate part? We need to put the dot. So put a dot, that means that these are associated with each other. And penta stands for what number? Penta stands for 5. So we've got 5, and hydrate just means H2O. Questions? Confusions? All right, then we will stop there for today and pick up with our other 2 categories of naming conventions next week, because I think we've got nomenclature after our exam.